So this is in some sense a grand tour, and it's one of these terrible audiences where we've got a whole range from super experts to not so experts, but I'll try to strike a happy medium. So let me just quickly review some stuff. So let's talk about extensions of Hodge structures. All right, so let's suppose we have V as a Hodge structure of negative weight. And I mean, it's okay to think of weight minus 1. That's the main case, but a lot of what I'm saying, about half of what I'm saying applies for any negative weight. And we'll assume that the integer lattice, Vz, torsion-free. You can also do it more generally. But all the examples I'll do will have the integer lattice underlying this guy as torsion-free. And then you can look at extensions as mixed Hodge structures, x1, of Z by V. So that just means mixed Hodge structures which map to Z. And I guess I know there's some super non-experts here. So you have a so-called mixed Hodge structure here. You have this guy here, and the quotient has a fixed isomorphism with Z, and the kernel has an isomorphism with V. Anyway, this guy is just going to be the complex part of V modulo F0 of V plus Vz. So I'll give, rather than explain this, I'll just give some examples. So everybody's first example, or one of the first examples, would be you take C as a compact Riemann surface, and V is just equal to H lower 1 of V, sorry, of C. So Vc is just going to be H minus 1, 0 plus H 0 minus 1. And this is the dual H0 of omega 1c dual. And that's the dual of the anti-holomorphic forms. And in this case, and I'm going to call this guy here, I'll call it J of V. Think of it as the Jacobian of V. And so here, J of V is going to be Vc mod, this is F0 right here, this number at least 0, H0 minus 1 plus Vz, but that's going to be just the dual of the holomorphic differentials mod H1Cz, and that's just the Jacobian of C. Right, so, and the and let me do another example. This is two. This is really Griffiths. Is that we'll take X to be smooth and projective over C, and we'll take V to be H2D plus 1, X Z of minus D. So this just means, well, this would be a Hodge structure of weight minus 2D minus 1. And this formally adds weight 2D. So this guy has weight minus 1. And this is partly a bookkeeping trick. And now in this case, J of V is Griffiths intermediate Jacobian, JD of X. I won't write it down, but it's a compact. Yeah, this guy is a compact. This guy is compact complex torus if V has weight minus 1. You can do it with lower weight. In the interest of time, I won't do any of those weights. But this is Griffiths intermediate Jacobian. And it's a compact complex torus, but it's not in general algebraic. And so, class of a homologically true. So if you have a x is above, so x smooth and projective, and let's take z, an algebraic d-cycle. So it's a linear combination of d-dimensional subvarieties. And let's suppose that the class of z equals 0 in h2d xz. So it's homologically trivial. And then this gives you an element. It gives you an element which I will call, what will I call it? Well, it gives an element, maybe I'll call it EZ, which is going to be in JDX. And I'll give you a very brief idea why you get such a thing. You could look at H2D plus 1 X relative to Z. This has a mixed Todd structure. It maps to H2D X. Sorry, it maps to H2DZ, which maps to H2DX. And the kernel here is H2DX. There's nothing here for dimension reasons. And now, mapping into here, you have a copy of Z. In fact, you have a copy of Z of D mapping into here, just basically the class of Z. This maps 0. So you pull back here and you get an extension of H2DX that corresponds to this cycle. Sorry? H2D plus 1, thank you. Yeah, right. So you get an extension of basically Z by this, and then you can just twist by minus D to put it in the appropriate place. And there's a very concrete description of how to do this. You can write Z equals the boundary of some 2D plus 1 chain, and you integrate this over the appropriate part of the Hodge filtration, just like you do in the case of Abel's theorem here. Yeah, so I'll give that as an example. Right, so let me just give one example of this. X equals a curve, so a compact Riemann surface. D equals 0, so we're looking at D cycles. So D is just going to be some Nj Xj. So Xj is a point in X. And and so this is our cycle. Maybe I should call it Z. And you can write, what does it mean to say it's homologically trivial? It's just this sum of the nj's are equal to 0. So this implies that Z is equal to boundary of gamma. And you get the extension corresponding to Z is going to be in the Jacobian of C. And this is just, as I mentioned over there, it's just the dual of the holomorphic differentials mod H1XZ. And this class here is just corresponds under this isomorphism to the integral over gamma. Gives you a function on holomorphic differentials, and it's only well defined up to periods. And so the general construction up here just generalizes that. Okay, here's another example which is more important. Well, that's an important example. But let me give you an example here that's more important for this talk. I mean, they both are. This is one basic example. This is the other. So again, I'm going to take C to be smooth projective curve. And I'm going to take X to be the Jacobian of C. So that's going to be my ambient variety. And for X in C, I get a map alpha. This is going to give me a map alpha which takes C into X, or C into the Jacobian of C. And it takes Y, goes into the divisor class of Y minus X. And so just use a point. You could use any divisor of degree 1 to embed the curve into the Jacobian. So that's an algebraic one cycle. And now I'm going to let I takes Jacobian of C into itself. It's just the involution that takes a point to its inverse. So this is a group. And I'm going to take the cycle. So I'm going to let C sub x, by definition, is just alpha star of the class of Z. Right? You just think of this as a formal way of saying it's a one cycle. And C negative, Cx negative, is defined to be I star of Cx. You just take its image under the involution. And this guy here, it acts as minus 1 on H1, and because of the ring structure, it acts as minus 1 to the k on degree k. This is a two-dimensional class, so these two guys are homologous, so I take my cycle to be Cx minus Cx negative. And this is homologically trivial. And this is known as the Teresa cycle. So, I mean, we're going to get to moduli of curves soon, and the point is this construction makes sense for any point in MG1. So, all right. So then this gives us a class. We'll have a class, maybe I'll call it new twiddle, is going to be a class inside the intermediate Jacobian of the Jacobian of C. Right? So this is our x. So it's, and this is the same as the Jacobian of the Hodge structure, which we write as lambda 3 of H1 of C. And we want it to be of weight minus 1, so it's this guy's going to have weight minus 3. We formally raise the weights by 2. Sorry, my hearing's on. No, it does. Okay, so I'm going to say more about that in a second. But the Jacobian of the curve embeds in here. Maybe I'll put I should put an x here. And if I take the difference between at x and y, the difference is twice the difference of x minus y. So later on, we're going to mod out this guy by the Jacobian. So, so what's a normal function? Well, so let's let v over x, so x is going to be smooth projective again, so or compact Kähler or whatever. Actually, no, sorry, I don't want it to be complete. Just, this is going to be smooth, some smooth variety. And let's take this to be a polarized variation of Hodge structure. So for the uninitiated, this means a family of Hodge structures indexed by T, so it's some flat bundle of, say, lattices, and when you complexify it, you have a holomorphically varying Hodge filtration, and then it has to satisfy all sorts of other conditions. But anyway, so it's a naturally occurring family of Hodge structures of weight, of negative weight, and less than 0, and typically for us, weight equals minus 1. I actually like doing it with all negative weights, but I don't want to annoy everybody. All right. So, and we'll assume, and let's assume VZ is torsion-free. I mean, even if it's not, it doesn't make much difference, but just everything's a little more technical. And so what we have is we have a family of intermediate Jacobians. You can take, I'll call it J of V. So this is just the family over T, whose fiber, it's a family of complex tori, whose fiber over T is going to be the Jacobian of this Hodge structure. Mm-hmm. And now, so if you have a section of this bundle, so a section of this bundle, J of V over T. So if you have a section, this gives point by, for each point it gives an extension into Vt is the fiber over T is a Hodge structure. It's going to give, it's an extension of mixed Hodge structures. Right? And if this is continuous, then this family of Hodge structures varies continuously. If it's holomorphic, this family of mixed Hodge structures will vary holomorphically in the appropriate sense. And okay, and it also gives us extension. I should have said this, local systems. So it'll be 0 into V into E into, say, Z of T into 0. So we've got both an extension of local systems, and on every fiber we've got a mixed Hodge structure. It's determined by this section, and we'd like to say that that is a variation of mixed Hodge structure. That, I'm not going to give all the definitions, but it's an axiomatization of the families of mixed Hodge structures that one gets from topologically locally trivial families of varieties. So definition. S is a normal function. What other people, I think, call admissible normal function, or if these two things together, star 2 and star 1, if star 1 and star 2 form an admissible variation of mixed Hodge structure over T. And this is, I believe, I started using this definition a long time ago, but it may be due to Saito. I'm not sure who first made this definition. But it's a very natural one. Griffiths had studied. There are many properties that this has to have, and correct me if I'm wrong, but there are various conditions on this section that it has to, its derivative, for example, has to satisfy. They were all written down by Griffiths in the 60s. Yeah. So some pre-version of this definition is due to Griffiths. And I say the most refined version of it's probably due to Saito. So I'll write the, for normal functions, I notice people have all sorts of notation. I just like MHST. This means admissible variations of mixed Hodge structure over T of Z by V. Right? So IES is in this guy here. And there are various conditions, and the conditions about what happens as you approach the boundary of T are by far the most technical. And okay, so there's a general construction. This is Griffiths. Of how you get such normal functions. So, for example, if you had x over t here, and this is a family of, say, smooth projective varieties. And suppose that you have, you've got a z contained inside x. So this is everything mapping down to t here. So this is a family of algebraic cycles. So you could write it as some, say generically as some linear combination of cycles, and if you restrict to each fiber, you get a cycle. And suppose they all the restrictions to each fiber have dimension d. So So I want this to be a family of D cycles. So this means, for example, if T was in T, up here you would have a ZT contained in XT, or really a ZT, an element of the D cycles on XT for each T. And that would be a D cycle. And I want to also assume that ZT is equal to 0 in H2D of XT, say Z. Right? So it's homologically trivial on each fiber. And now we have our, so each ZT then would give a point. So each ZT gives a point in JDXT. So this is the appropriate intermediate Jacobian of the fiber. So what we want to do is do this in a family. So I'm going to write, say, JD over T. This is going to be the family of intermediate Jacobians. So over T, its fiber would be JT of XT. Okay, so JD of XT was the Jacobian of H2D plus 1 XT. Right. Just to remember that. All right, and so this, for each T, you get a point in this. So you're going to get the class of ZT is going to be an element of this for every T. So this is giving you a section here. And this section, the theorem is that this section is a normal function. So theorem is that S is a normal function. Or to use language that, say, Brosnan and Perlstein use, it's an admissible normal function. Right? So this is a combination of work of Griffiths, and so you can get it from an old result of Steenbrink and Zucker. The hard part is the admissibility. And there's Guillen. And also, if you want to kill it, you can hit it with Saito. Morikiko Saito. Right? So anyway, this is an example of a normal function. So families of homologically trivial cycles give you normal functions.
The Saito version, is that just sort of taking your proof that you did on?
Yeah, I mean, right. So if you took this, the way I think of it is if you take, I don't know if it's still there, but if you took the sort of exact sequence of the pair Z with, the cycle, you want to say that it's an admissible variation. So, I mean, I guess his theorem says what the 6 functors are preserved mixed Hodge modules, blah, blah, blah. All right. So let's yeah, the result of Steenbrink and Zucker said that if you had a topologically locally trivial family of smooth varieties, then the corresponding local system was an admissible variation, and that's all you need. All right. So let's talk about normal functions now over sorry?
No, you would apply that statement to the complement of Z.
Yeah, exactly. Normal functions over MGN. All right, so we'll take 2G minus 2 plus N to be positive, and MGN is equal to the moduli, I'll say space, but I really mean moduli, stack, orbifold, whatever, moduli space of N-pointed smooth projective curves of genus G. So typical thing in here would be a curve with n labeled. So I take, like most people, I take the points to be labeled, points that are distinct. And so this is also the mapping class group of type Gn, the quotient of the appropriate Teichmuller space of type Gn. I'm not going to dwell on this stuff here. This is a generalization of the upper half plane, or a generalization of Siegel space, so this is contractible. And this guy here is the mapping class group, so gamma Gn is just the group of connected components of the group of orientation preserving diffeomorphisms of a surface of genus G. So you just take a surface of genus G that has on it n-marked points. So, and it has to fix point-wise the n-marked points. And so this group is acting very nicely on Teichmuller space, much the same way as SL2Z acts on the upper half plane. So gamma Gn is equal to pi 1 of mgn. Okay. Right. So we want a variation of hot structure, or we want a whole bunch of them. So let's take C over mgn is the universal curve. And just in case there's any doubt, it's the universal complete curve. I don't remove the punctures. I don't remove the points. And so let's call this F. And so I'm going to take H to be, I want a variation of weight minus 1. So I'm going to take R1 F lower star of Z, and I'm going to twist it by 1. So this has got weight minus 1. And you can think of this as saying over the point, if you look at over the point, say, Cx1, xn, the fiber is just naturally h1 of C, Z. Right? So this is the fiber of this local system over this point. It's h lower 1. So it's got weight minus 1. Yeah, and the polarization is, we need the polarization. The polarization is the intersection pairing. So it's H1 tensor H1 of the curve goes into Z of 1. All right. So let's look at some examples of normal functions over MGN. So so I can take J of H. So this is over MGN. This is just the universal Jacobian, because the Jacobian of this Hodge structure is just the Jacobian of the curve. And let me just do this over MG. No, I'll do it over MGN. And now I take the point here, so the fiber over the point CX1, XN here is the Jacobian of the curve, and I'm going to take the section kappa J. So I'll take a section here. I'll call it kappa sub J. Kappa sub J of C x1 xn is going to be 2G minus 2 times xj minus the canonical class of the curve. Right? So you can take any canonical class because the point in the Jacobian corresponds to this, just depends on the divisor class. Right? So these are all normal functions by the construction we had before. Yeah. So more interesting example is the second example is, so this is 1. So I'm going to take the Jacobian of lambda 3h minus 1. So this is, and I'll think of this, say, over mg1. And I'm going to take a normal function here, and I'll call it nu tilde. And its value on at this point here is going to be the point corresponding to cx minus cx negative. Right, so nu takes this guy to this. So it's the normal function corresponding to the Teresa cycle. Actually, I'll make a remark here. There, you can construct a whole bunch of normal function sections of this. You can do it using the Teresa cycle. You can use it using the Gross-Schoen cycle. You can also Gross. So, which is a cycle in the third power of the universal curve with itself. Or you can also look at the group algebra jx minus jx cubed. It'll also give you a section where jx is equal to the augmentation ideal of pi 1 of cx. These are all normal functions, and all sections of this. So one question is, what relation do they bear to each other? Hang on. No, I'm doing it as a stack. So if you like, if you want to be careful, well, I mean, you can either work equivariantly over Teichmüller space, or you can just choose any level that's 3 or more, and you work so it's equivariant under the action of the finite symplectic group. It's just exactly what you do with the upper half plane. And but even, for a lot of what we're doing, also once the genus is 4, the curves with automorphisms have high enough codimension that they don't affect the fundamental group. All right, and so there's another one I want to look at. So here's a related fact to what you asked me before. Is the fact is that if you looked at, so I think I was calling this cycle. Let's call this z of x. So if you look at z of x minus z of y, the class of this in the intermediate Jacobian, yeah. So first of all, I need to remark, one is that there's a map from h into lambda 3h minus 1. It's basically cupping with the Kähler class. And now, or wedging with whatever, the intersection form. So this gives you a map of j of h into j of lambda cubed h minus 1. Right? And so I'm thinking of the Jacobian as sitting inside this intermediate Jacobian. And the second thing is if I look at zx minus zy, so what happens when I change the point? It's going to be 2 times the class of x minus y. Right? So this means if I mod out the Jacobian, the intermediate Jacobian by the Jacobian, I get something independent of the point. So this says that, so 3 is nu of x equals nu of y, and I'll just call this nu. Nu of c is going to be defined by nu twiddle x minus element of the Jacobian of lambda 3h minus 1 mod h. Right? is independent of x. So this guy here gives me a normal function, which I'll call nu. So we get a normal function here over mg, but we have to look at the normal function of, it's basically the primitive part of h3 of the Jacobian. Right? We get a normal function here that takes the sort of base point independent part of All right, so let me emphasize something here. This normal function, and in the case of n equals 1, basically these guys are the important guys to think about. You can do other things, but you can express them in terms of these guys. For example, you could look at the difference between 2 points, but up to tensoring with q, they can all be expressed in terms of the guys I've got on the board. All right? Right. All right, so what we can do here is, so here's the construct. So if V is an irreducible, and let me point out here, we have a monodromy representation from the mapping class group into SPGZ, or what some people like to call SP2GZ. And this is basically the map on pi 1 from MG to AG induced by the period map. And so this is actually easily seen to be surjective. And if you have a representation of the algebraic group SPG, it gives you a variation of Hodge structure. So to each irreducible SPGQ module V, we have a polarized variation of Hodge structure V over mg, or mgn, it doesn't matter. It's actually pulled back from ag, unique with monodromy, I'll just say with fiber V. Right? So fiber V as a gamma GN module. And it is unique up to Tate-Twist. It's unique up to Tate-Twist. This is not hard to see. So let me write down all normal functions over MGN that correspond to these variations. Okay, you can take any integral form of it. So I'm going to just talk about things up to torsion. Yeah, so yeah, let me just, there's something I'd like to get out of the way at the moment. So every normal function in x1 and we take some z version of this, okay? It doesn't matter which one, extends to mgnc. This is equal to the moduli space of gn curves of compact type. So these are the curves whose Jacobians are actual abelian varieties, not semi-abelian varieties. Equivalently, they're dual graphs of trees. So if you're a topologist, you would picture them like this. They're dual graphs of trees. Right? And you can put points wherever you like. This is of compact type. Anything like this, or even like this, these are not of compact type because their dual graph has a circuit. All right, so every this is an easy argument in Hodge theory. All right, so let's talk about the classification. So if V is an irreducible polarized variation of Hodge structure of this type, of the type I just discussed, over MGN of, say, negative weight, actually of any weight, and if G is greater than or equal to 3, so we need this condition here, then the set of normal functions x1 I could just as well put C here. I get exactly the same thing of Z, say, actually I'm going to put Q here, QV is equal to 0 unless and here I can use the more general definition of normal functions. Just x1 in the category of variations, I can give this any weight. So the only time you get something non-trivial is that unless either 1, V is equal to H, in which case this X group of Q by H is isomorphic to Q to the, well, it's actually equal to Q times kappa 1 plus Q times kappa n, so it's Q to the n. And 2, V is equal to lambda 3 H minus 1 mod H. And in this case, and here, X, where X1 of Q by V is Q times the normal function nu, the sort of base point free version of the Teresa cycle. And I think over here, I mentioned there are all these normal functions. Well, this tells you, I mean, I think you can do this one directly quite readily, but the Gross-Schoen cycle and the Teresa cycle give you the same up to a point, up to a multiple in the intermediate Jacobian. What's less obvious is it's the same as the mixed Hodge structure on the first non-abelian quotient of pi 1. And you can compute the multiples. Sorry?
That can be 0 if you already.
Sorry?
That can be 0 if you already, you're saying you know it's not 0.
No, yeah, they're non-zero. And you can check the multiple just by computing the monodromy around any one boundary component. And that statement about the equality here is sort of something that goes back to Bruno Harris and Mike Pulte. So, but you could, and I should say what lies behind this theorem, because actually then this is a year in topology of varieties, so it's actually topological. So main input, I mean, one part is just abstract Hodge theory. And the other part, and two, this is really the main part, is the fundamental work of Dennis Johnson. So what did he do? You've got the mapping class group maps to the symplectic group, and the kernel is the Torelli group. And so this is Torelli group. And what Johnson did is compute the abelianization of this guy. And it's a highly non-trivial theorem. There's still no really good proof. There's 3 proofs out there. It's very deep, but just to give you an idea, what is H1 of just TG Q. In fact, this is something I learned about at the Institute in 1985, I think. Anyway, it's lambda 3 H mod H. Right? This is where it comes from. And if I put, actually, and if I put TG in, it's this. Rationally, it's this plus H to the n. And you can naturally give it a Hodge structure, although it's not H1 of any variety. And this is a naturalized, for each choice of a curve, this has a Hodge structure, and this guy has weight minus 1. And that's basically where this comes from. So this is a highly non-trivial theorem. We're still working on getting a good proof. In fact, to go beyond this theorem, and I may say something at the end, you may like to do this in the prim case, you need the prim analogs of this, and nobody has any idea of how to do those, or I don't. That's one reason for trying to find a good proof of this theorem here. All right, so section 5 is, I want to give you some applications, class of a normal function. So, yeah, I'll write this down. We don't really need this, but there is an exact sequence, which is X1 mixed Hodge structures, say of Q by H0 of XV. So here V is a polarized variation over X. X is just smooth. This maps into the normal functions over X, X1. And then this maps into, so this is extensions of variations. You can just map into extensions of local systems, and this will map into H1XV. And in fact, it lands in what I'll write gamma. So gamma here means Hodge classes. So it's just HOM, mixed Hodge structures, Q blank. It just picks out the Hodge classes of type 0, 0. And so this tells you that, so if you have a particular normal function in here, so what do we call the normal function? Nu. So a normal function here, nu in here has a class I'll call C of nu in here. It just tells you what the underlying cohomology class corresponding to the local system is. And so, and let's now assume now that the weight of V is minus 1 for the rest of the talk. And so you've got a polarization. So what's the polarization? It takes V tensor V into Q of 1. And so this induces a map, and if you think about it, this is skew. So this is skew. So it induces a map from S, the second symmetric power of H1XV, into H2 of XQ. You can do this integrally too. For some reason, I wrote it down rationally in the notes. But you've got this thing here, and now you can take C of nu, and I'll write tensor to, and you can take it to its, I'll just write this as C of nu squared. Right? I'll think of this guy as being a class in H2. In fact, because this was a Hodge class here, this is a Hodge class here. So in fact, it's a Hodge class. So already you know there's a line bundle. If I'd done it integrally, there would be, I could say straight away there's a line bundle. So I want to tell you how to get that line bundle, and this is where bi-extensions enter. So part of my goal here, I haven't left myself much time, is to explain this bi-extension and high jumping. But anyway, we've got this here. So this gives you a line bundle. holomorphic line bundle. So, all right, so I wrote in the notes here what's the significance of this class and what properties does it have. So a theorem, yeah, so we're going to suppose that nu, so this is a perfectly general theorem. Suppose nu is in, it's a normal function, x1 mhs over x. And now I've written z times v just to confuse you. Well, to confuse myself. I could have done this integrally up here. And x is equal to x bar minus d, where d is a divisor with normal crossings. It doesn't have to have simple normal crossings. And x is smooth, the usual story. Then, 1, there is a line bundle. I'll call it B nu over x bar. And I realize I've been a bit sloppy here. Sometimes I'm going to refer to this as a C star bundle or a GM bundle, which is canonically metrized over, and this is key here to get this right, x bar minus d singular. So d singular is where d, so it's an example is going to, we're going to have an example with MGN, delta 0 intersects itself. And it intersects itself in curves that look like this. Right? These are curves that you can smooth two separate ways into delta 0. And this is the locus of where delta 0 intersects itself is going to be part of the singular part of this boundary divisor. Yeah, and because in our case d is just going to be delta 0, x bar will be MGN, and the open part, x, will be just the curves of compact type. Okay. So it has the property. So property is that C1 of B mu restricted to x is equal to twice the class, this class. And I have to put a warning in here. The metric may not be smooth. The metric is continuous, but may not be smooth. And I should say some of this stuff here goes back to a student I had who couldn't get a job, but he wrote a great thesis in 1990, Dale Lear. And he went into computer graphics instead. But anyway, 2, the curvature of B is a non-negative 1-1 form. I should say current on x bar. Okay, so this is already gives us some interesting stuff here. Yeah, I'll just say I've got a whole pile of remarks here. So this is a composite of results of various people. Some of this is due to me. Some of it's from Lear. So this extension is due to Lear. Then there's Brosnan and Perlstein. So and actually, Greg reproved all of Dale's results in sort of more modern way, and Perlstein. But these guys have been a great help in sort of tidying up. And later on, I'll just add here Robin de Jong, because I made several conjectures here, and between these guys, they've proved them all. Yep. And Robin de Jong is just in the case of MGN bar. All right, so All right, so, right. So let me give you some applications and examples. Okay, so here's a theorem that I proved with a guy called David Reed. So nu is the, I'll call it the Teresa normal function, right? One of the very basic ones. So this is in x1, z by lambda 3h mod h. Right? It's this guy here. And now let's compute what this class is. So C1 of B nu is equal to 8g plus 4 lambda minus g times delta 0 minus 4 times the sum h equals 1 to g over the h g minus h times delta h. So these delta h is the class of curves that are the boundary divisor, this boundary divisor. Delta 0 is, of course, the class of these guys here. Lambda, so this is delta h, delta 0, and lambda is equal to the determinant of the Hodge bundle. But this divisor was already known. This is the Moriwaki divisor. Okay, so he found, I don't know what his motivation was, but he found this divisor and he proved that it had non-negative degree on every curve inside mg that was not contained in the boundary. But it's sort of funny, what I knew here, this positivity and so on, gives a version of Moriwaki's inequality that was weaker in some ways and stronger in others. I could allow curves to be contained in the interior boundary components, the ones that stay in AG. But I couldn't get some of the other cases, but I made some conjectures, and that's what these other guys have resolved. But so this is theorem, this is improved Moriwaki. Is that, so if f takes t into mg bar is a curve not contained in not completely contained in delta 0. The image can't be contained in delta 0, then the degree of the Moriwaki divisor on T of Moriwaki is greater than or equal to 0. In fact, with this high jumping stuff, which I don't think I have time to talk about, you can actually show that it's, for curves that hit the boundary in very singular part of delta 0, you can bound this away from 0. Yeah, maybe I'll stop here, but I will mention the things that I'm not going to mention. So, yeah, maybe I'll say very, very briefly. So, what's other stuff? Other. One is Eliashberg's problem. I'll tell you what it is. I won't tell you the answer, but when I tell you, it'll be clear what it has to do with normal functions. So if you're on MGN and you have integers d1 up to dn that add up to 0, you can take a section here which is sum dj xj. And Eliashberg's problem was to compute the class of the pullback. So let's call this f sub d. So compute the class of fd star of the 0 section. And I did this in case of compact type, and I computed the answer in cohomology. Other people like Sam Gruszewski and what's his collaborator's name? Zakharov. Shows that valid in the Chow ring, and they also computed what happens when you put the smooth locus of delta 0 in there, which is quite hard. Anyway, so this one, but the point is here, this is a normal function, and you can use this classification. You just write this guy as a linear combination of the other things and use, I wrote that formula. This is a similar formula for kappa, and you just grind away and you get out the answer. Height jumping I would like to talk about, but I won't because I don't have time. And there's other stuff related to the tautological ring. This work of Morita on the tautological ring. All of the tautological ring comes from normal functions. And there's other things I could mention, but I'll stop. Exactly. In fact, there's right. And so, right. In genus, so, I'm working with Francis here. In genus 1, almost every irreducible representation of SL2 has non-zero cohomology, modular forms. Genus 2, I think is strange. The answer depends on the level, but it appears, so this guy, what's his name? Peterson? He showed that I think basically you only get this representation. So basically the highest weight part of S2 lambda 2 has non-zero cohomology. If you go up to level 2, I know you get this guy. And I think if you go up to full level 2, you get this to the 2G plus. You get this guy, if you look at the cohomology, has this dimension. I don't know if any other representations can have non-zero cohomology if you go up to a level. So in genus 3 or larger, if you go up to a level, you don't pick up any more cohomology. What I'd love to know is about the prim construction. So if you looked at the classical or non-classical, whether you can pick up more normal functions there. I don't think anybody has any idea. I mean, it's hard to interest topologists in this problem, but they seem to be the people that can compute this cohomology. Certainly you can use these to construct normal functions, but then, I haven't tried. It's that far because there's just so many questions. Another example is hyperelliptic curves, which I've thought about quite a bit, and we're getting somewhere on that. There's some of these students of, I got a student, and some of the former students of Benson Farb proved some results, But if you ask me to guess what's happening with hyperelliptic curves in higher genus, these are the only two representations that have any H1. At least if you, probably always, but I can't prove it. It's hard. Okay.